I will summarise those answers. You should have them already. Last week we went through a case where we had three signals, A, B and C. Okay, you should have this, no need to copy. And if you remember, we had different equations for those signals, at least for two of them. Right? And all three of them were different equations. I'm not going to write the equations, but in summary, the equation for signal A, I think you have, it looks similar to this one. It has two components, sine something plus a third sine something. So I would say there are two components in equation A last week. Signal B also had two components and signal C had three components. So although they're not exactly the same, it's the same shape. From last week we had three signals, A, B and C. Signal A and B looked like this, had two sine components, and signal C had the three sine components. And we set a frequency for those signals, and signal A we said was 1 kilohertz, 1000 hertz. Signal B we changed to 2000 hertz, and signal C back to 1000 hertz. So this is summary from what we came up with last week. From the equation and from the frequency we know, we could calculate the bandwidth because it's the frequency of the largest component, or the highest frequency component minus the lowest frequency component. And we calculated signal A, what was it? Someone has their notes. Signal A had a bandwidth. Signal A, bandwidth of A, 2000 hertz. Just want to summarise. And we did it also for signal B, and we got 4000 for B and 4000 for C. And the other thing, the last thing we calculated was the data rate. And remember the data rate, we were assuming within one period we could send 2 bits. That is because every high signal represented 1 bit and every low signal another bit. So in one period we have a high and a low, therefore 2 bits in that case. We know the frequency of our signal. We know the period will therefore be 1 millisecond, and we got 2000 bits per second. I'll remove the units just for space, 2000. And for the signal B, we got 4000. And for signal C, back to 2000. That's from last week. And if you plot those signals, they look shaped like this. A and B shaped like the top one, and C like the bottom one. And then the point is not so much about those values, those specific values, or about the exact signals. The point is the trade-offs between them. When we design or choose a signal, how does it impact on performance? We see, let's look at the bandwidth and the data rate first, comparing signal A to signal B. They were the same equation, but just different frequencies, resulting in different bandwidths. And the benefit of signal B versus signal A was that it increased the data rate. We want high data rate, okay? We want to send our bits as fast as possible. Signal B gives us a higher data rate than signal A. So that's the advantage of signal B in those, when we compare the two. The problem with signal B is that it occupies or uses more bandwidth. Now bandwidth, the range of frequencies which we can use, is limited. There's only some frequencies that we can use. And how it actually works in practice is that governments control which frequencies you can use for which purposes. Because there's competition, that is, some companies want to use the same frequency, it turns out that frequencies have some cost involved. The larger the bandwidth or the larger range of frequencies you use for your signal, normally the larger the cost involved. We want to minimize the bandwidth we use, smaller bandwidth, but maximize the data rate. A is good because it's got a low bandwidth. B is good because it's got a high data rate. So there's no one best solution there. That was one trade-off, data rate versus bandwidth. The other we saw was if you compare A versus C, which is really the top one versus the bottom one on the screen. We had the same frequency for the signal, but A uses a bandwidth of 2,000 hertz and C a bandwidth of 4,000 hertz. So C is worse than A because it uses more bandwidth. That's a bad thing about C. They deliver the same data rate. So there's no advantage of C from that perspective. C is worse bandwidth, same data rate. What's the difference, or why would you use signal C? Well, what was the difference? We had a different equation with 3 components. It resulted in a slightly different shaped signal. The bottom one is C, the top one is the shape of A. What's the benefit of the bottom one? Well, we summarise, or we finish with this point about accuracy as well. We can talk about the accuracy of a signal. And that's what we'll try and explain more today in this lecture. That is, in the presence of noise in the system, and we'll explain what noise is, in the presence of noise, the received signal will be different from what's transmitted because there will be noise as well. The goal of the receiver is to distinguish from the received signal what bits were sent. The more accurate our transmitted signal is, the less chance that the receiver will make a mistake in recognising the bits of the received signal, the less chance of errors. And that's what we're going to try and explain today, of how the signal shape, why is the second one more accurate or better than the first one in terms of errors. For now we're just saying that signal C is more accurate than A, or less errors will occur with signal C than signal A. Signal C has a higher bandwidth, that's bad. Same data rate, well, there's no advantage. The advantage of signal C is there'll be less errors, in theory, when we transmit that signal. So that's what we need to talk about, of what causes these errors and why one signal is better than another. This example is very similar to what we went through in the class. So it's just different values, slightly different setup of the question, but you have to do the same calculations. The larger the bandwidth we use, and we see that with signal A versus signal C, the larger the bandwidth we use with the same other conditions, the more accurate signal we achieve, we generate. And that's shown here. In this simple example, we have some bits we want to send. And how we transmit those bits is we use some digital signal, which the scheme says that if I want to send a bit 1, I will send at a low level and a bit 0 at a high level. So we get this pulse, stream of pulses, which really has 2 pulses when we want to send a bit 0. But in this example, we transmit an analog signal to represent that digital data. And the bottom ones show different analog signals when we increase the bandwidth of that signal. If we use a bandwidth of 500 hertz, the analog signal generated in this example looks like the green sine wave here. The ideal signal is the 2 pulses here at the top. If we transmit with a simple sinusoid with a bandwidth of 500 hertz, the transmitted signal is the green one here. All right, you can see you need to compare this one to the ideal signal and see, does it match, does it resemble the same signal? Well, the resemblance is only that, okay, at these 2 points it's at its highest. If we increase the bandwidth, keeping all the other factors the same, increasing the bandwidth, we see the generated signal gets closer and closer to the ideal signal. So a bandwidth up to 4,000 Hertz, we've almost got this perfect two pulses. Of course, we have some variations here. The point here is that increasing the bandwidth increases the accuracy of the signal we transmit, and we're going to show that also reduces the chance of errors. But of course, increasing the bandwidth, with all the other factors the same, increases the cost. That's bad. So we have a trade-off between bandwidth, data rate, and errors. Or accuracy. More accurate, less errors. Less accurate, more errors. And that's summarised here. I think we've covered this enough last week and a little bit today. Bandwidth is a limited resource, therefore the greater that we use, the greater cost involved in general. The greater the bandwidth, the greater the data rate we can achieve. We want to get high data rate, we want a low bandwidth. And the greater the, although it's not said here, the greater the bandwidth, the greater the accuracy of the signal and less chance of errors. We're going to talk about what are transmission impairments shortly. Before we do, we need to talk about some terminology of analog versus digital. What is the difference between analog and digital? If you need to describe something as analog versus digital, how would you describe the differences? I think in one of our first lectures we had something about it. Change. How would you describe something that is analog? Again? Electromagnetic, but in simpler terms, what analog versus digital? Analog changes continuously over time, something that is analog. Digital, discrete values. It's at one value, then immediately at another value. That's the basic difference between analog and digital. We can distinguish, in this topic we're going to distinguish between analog and digital data. The information we want to send to someone, we talk about as data. It can be either analog data or digital data. Similar, the signals that we send across our transmission system can be analog or digital. We want to get data from A to B. The way that we transmit data from A to B is to transmit signals. The data can be analog or digital, and the signals can be analog or digital. And we have another concept of analog or digital transmission, the way in which we propagate and process those signals. We're going to go through some simple examples of each of these to demonstrate the differences. We'll go through reasonably quickly because there's some basic concepts. So analog data, focusing on data, the information we want to get from A to B. Analog data varies over time, continuously. Examples, voice, video, some sensor data, some device which is recording the temperature in some room. It continually records a value. It's continually changing over time. Digital data take discrete values. Text, integers, bits, digital data. Here's an example of analog data. It's the one we use all the time. Audio. I am communicating analog data to you in this lecture. The audio or the speech is an example of analog data. What this diagram shows is the spectrum of different types of analog data or audio data in this case, where we have the frequency and some signal strength. It's given in decibels, but the higher we get, the stronger the signal. And what it's showing is that if we focus on the solid green line, that is the range of frequencies that typical speech uses. When someone talks, They're generating data at different frequencies. And the typical range goes from around 100 Hertz up to around here, which is what? Because there's a logarithmic scale, maybe 9,000 Hertz. So from several hundred Hertz up to several thousand Hertz is the typical range of speech. When you talk, you're generating data in those frequencies. Strongest in these areas, which is around, whatever is it, 300 Hertz up to 3,000 or 4,000 Hertz. But sometimes even the low frequencies can be picked up when someone talks. So that's an example of analog data. Music, another example of analog data, covers a wider range of frequencies. If you think not just people talking or singing, but instruments and so on, there can be much lower frequencies, up to tens of Hertz. And higher frequencies, up to 10, 20, 30 kilohertz. And usually we can distinguish that with our ears. When we hear music, we can hear the lower frequencies and the higher frequencies compared to someone talking. So they are examples of data. When we send that data, we may use different transmission systems to send that data from A to B. One example is radio. Okay? You're in your car. What's your favourite FM radio channel? Someone name a channel. 107 point something usually. 107.0. So FM radio channels are usually given a name, but also you often know the frequency. Okay, 107.0 megahertz, in fact. In fact, that FM radio channel transmits the music and the audio across a range of frequencies, usually centered about, let's say, 107. When that radio channel transmits, there's a tower that transmits, your car receives. It's called 107.0. It's referring to megahertz. It's actually transmitting frequencies plus or minus 107.0 megahertz. The bandwidth is about, and we see here, the typical bandwidth of FM radio is about 20 kilohertz. So in fact, it's not transmitting just at one frequency, it's transmitting the signal, which has a spectrum or a bandwidth of around 20 kilohertz. So a typical FM radio transmits signals with a bandwidth of 20 kilohertz. And that's what's shown in this dashed line here, the upper limit of FM radio. It's around 20 kilohertz. Whereas AM radio transmits up to, maybe this is 8 or 9 kilohertz, the bandwidth. What that means, AM radio transmits frequencies with a bandwidth of about, or less than 10 kilohertz, FM up to 20 kilohertz. When you listen to, or when music is generated, music contains frequencies up to 20, even 30 kilohertz. So most of those frequencies of music can be transferred in an FM radio channel, but in an AM radio channel, which only transmits up to 10 kilohertz, some of those frequencies of the music are not transmitted. And that's why it sounds worse in an AM radio channel compared to an FM radio channel. It doesn't have as wide a bandwidth to carry those frequencies we need. So just an example of data, the green lines, and two example transmission systems which you know about, FM and AM radio, which have different bandwidths. And therefore they can only carry the signals up to that bandwidth. FM up to 20 kilohertz, AM up to around 8 or 9 kilohertz. AM cannot carry music in these high frequencies. FM cannot carry music in these very high or relatively high, very high frequencies of music. That is, FM can carry most of the music, AM not so much, and therefore the lower quality. So audio is one example of analog data, video as well, and there's other examples, censored data and so on, but continuously generated or varying data. Digital data, text, bits. An ASCII table is an example where, well, not an example of digital data, but an example of how we can convert characters, letters in an alphabet, into some binary value. So text, the letters in some message, change continuously over time. Normally we represent digital data not as characters and so on, but as bits, zeros and ones. What's the value of A? The letter A, lowercase a. What's its value? No, the way that we read this table is we read the column first. A, 1, 1, 0, 0, 0, 0, 1, the row. That's in binary, of course, base 2. In decimal, anyone have a calculator? 97. 64 plus 32 plus 1. Okay. You've seen, or you've used probably ASCII tables to represent, when you're programming sometimes you need to look at numbers in the ASCII decimal value. But of course a letter using this table can be represented as a 7-bit value. So we can represent many things as digital data. In fact, we'll see later that we can convert analog data, and we often do, convert analog data into digital data. Take your voice, record it on a computer and save it as a binary file. So that's an example of converting from our original analog data into digital data. So we have analog and digital data that we want to send across a network. We can transmit our data as either analog or digital signals. Remember, we don't send the data, we send signals that represent the data across our link or across our transmission medium. Either some continuously varying electromagnetic wave, an analog signal, some waveform, or some digital signal like some voltage pulses. And that's what's shown here. Transmit at -1 volt for some period of time, and then, or put on a line a negative voltage, and then change to a positive voltage and a negative voltage and so on. We could use this scheme to represent our data. So this is an example of a digital signal where we have discrete changes of the values. In many cases, using digital signaling is considered cheaper and generally considered better than using analog signaling. It's just as cheap to generate the circuitry that creates those signals for digital signals than analog signals. Interference comes from other transmitters. When I'm talking to you and other people are talking, then those other people are interfering with what you receive. So digital signals are better to cope with interference than analog signals. Digital signals, the bad thing, so they are positives about digital signals, cheaper, less susceptible to interference. The bad thing normally compared to analog is that it suffers more from attenuation. What's attenuation? What's attenuation? What does the word mean? Attenuation. something attenuates, when we talk about signals, it gets weaker. It gets weaker. And that's what we're going to talk about in some depth in a moment. That is, they get weaker faster compared to analog signals. So there are trade-offs between using analog and digital signals. So we can have either analog or digital data, and we can transmit that data as either analog or digital signals. So 2 types of data, 2 types of signals, 4 combinations we can have. We transmit our data as signals. We'll go through those 4 combinations and give you examples. Using your home fixed landline telephone, not your mobile phone, but if you've got an old style phone at home, that's an example of sending analog data, your voice, as analog signals. Because in fact your telephone transmits onto the telephone line analog signals. You're at home. And you have a telephone at home. And you plug the cable into the wall at home. And that cable in the wall actually goes under the ground to usually some telephone exchange. Let's ignore from the rest onwards. So when you pick up the telephone and start talking, you've called someone, you're generating or transmitting analog data, your voice. And what the telephone does really is converts that audio into some electrical signal which is transmitted as an analog signal across the cable and out to some telephone exchange, and maybe then onwards to the destination, to the person you're talking to. So an example of using analog data and signals. Most people also have a computer at home. And if you want internet access, how do you get internet access at home? Anyone have internet access at home or in their dorm? How do you get your internet? Don't say Wi-Fi. Don't say mobile phone. They'll come to them in a moment. What other way? If you don't have Wi-Fi, you don't have your mobile phone, but you want internet access at home or in your dorm, you need to pay, and you use what? What technology? A modem. You use something usually referred to as ADSL. You have your computer at home, then you have this other box, a modem. I'll write it out here. Some box which your computer connects to via a normal LAN cable. And where does that box connect to? Anyone have an ADSL modem at home? Hands up. Anyone? Anyone have an ADSL modem at home? See if people can answer this. Okay, let's try differently. Anyone does not have an ADSL modem at home, put your hand up. Anyone who does not have one at home that they don't use, put their hand up. Okay, in that case everyone does. Then where do you connect your ADSL modem to? To the phone, not to the phone itself, but to the socket in the wall, okay? In fact, you connect it to the, so here's your socket in the wall. Usually you have a small box, a filter, that your phone connects into and your modem connects into. And they both go into the wall and connect out to the telephone network. The signals sent by the modem and out onto the telephone line are analog signals. The telephone line only carries analog signals. But your computer generates digital data. Your computer generates zeros and ones. So we think of you using your home internet as a case of you sending digital data, zeros and ones, which represent web pages and so on, via the modem, which converts to analog signals, and those analog signals are sent across the telephone network. So a modem converts the digital data into analog signals, and a modulator converts the digital data into analog signals. A demodulator converts the analog signals back to digital data. So a modulator and a demodulator becomes a modem. So there's an example of analog signals and digital data. Of course, you don't always have to send analog signals. You can transmit in some networks or some systems digital signals. Who has a mobile phone? Hands up. Okay, everyone. A mobile phone uses digital transmission and sends digital signals. From your phone to the cell phone tower, the base station sends digital signals. They're represented as electromagnetic waves, but we think of it as a digital signal. But when you talk on your phone, you're creating analog data. Okay? You talk, that's analog data. So your mobile phone has what's called a codec, which converts your analog data into digital signals to be sent. So there's a different third example. Where else do you use codecs? Where do you use a codec? Where have you heard about codecs? What type of files? Music files, video files. Well, not everything. It's usually audio and video files. You may hear about codecs. Well, a codec converts the analog data, the audio, the music, the video, into some binary format. MP3 is a codec that takes music, the analog data, and converts it to save it as bits, zeros and ones, as a digital data. So a codec goes from analog to digital. And the fourth case, in some systems, we can transmit digital signals when we have the input digital data. A computer connected to the LAN can transmit digital signals out onto the network. So all digital in that case. Computer generates zeros and ones, they're sent as some digital signal across the network. 4 different cases here. In not the next topic, but the one after, is called signal encoding techniques. We're going to look at how do these conversions work? How do we take our analog data and create digital? How does a codec work? How does a modem work? And so on. So we'll look at the ways for converting later. Now we're just mentioning that there are 4 different approaches. So analog data, analog signals, digital signals. Last thing, that just summarizes. We can talk about analog and digital transmission. The best way to think of this is with an example looking at across a set of links. Let's try the example of our audio system in this room. What's the input to this? When I'm lecturing, what's the input? What type of data? When I'm talking, I'm creating analog data. Okay. And the microphone takes the audio, the vibrations from the audio, and generates a signal. Turns out it's also an analog signal which goes to the wireless transmitter in my pocket, which sends an analog signal to the receiver on the desk, which sends via a cable down on the bottom of the desk. There's an amplifier. sends an analog signal, and the amplifier sends across some cables, and there's some speakers on the walls, both analog signals. And then the speakers generate audio signals which go to you. There's an example communication system. In this case, we're dealing with analog signals all the way. There's no converting to binary. The transmitter receives an analog signal, transmits an analog signal. What's the difference of me talking with a microphone? It's louder when I use a microphone. Why? There's some amplification going on. In this component at least, it's increasing the strength of the signal. Why? Why do we do that? To make it loud, to make it hearable by all the people in the area. If I don't have the amplifier, the people at the front will hear, but the people at the back, it may not be so clear. It'll be harder to hear. With the amplifier, we make it so that it can be heard clearly at the people at the back as well. In fact, everyone in the room. Why do we need the amplifier? Well, our signal attenuates as it travels. It gets weaker. When I talk, if I don't have the microphone on, the people at the front hear it louder than at the back, because as the signal travels, it gets weaker and weaker and weaker. It attenuates. So in an analog transmission system, and this is an example of an analog transmission system, we send analog signals, and to make those signals to be received by the receivers with strong strength, we use amplifiers where needed. We increase the strength. Although I haven't drawn it, one way I often draw signals, you transmit at some magnitude, and over distance it gets weaker and weaker. It gets smaller, the magnitude does. What an amplifier does is takes the received signal and increases the magnitude, and then it gets received at a level that's reasonable. Analog transmission system takes analog signals, and those signals are propagated through amplifiers where necessary to cover some large distance. If I want to send some data from here to the US through under the sea, under the Pacific Ocean, there's some cables under there. The signals are transmitted across those cables. After some distance, maybe 50 kilometres, the signals get very weak. So in the bottom of the ocean, they have amplifiers down there, or they could have amplifiers. So we transmit to an amplifier, and that increases the signal. Goes 50 kilometres, gets weak, 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 and they increase again. That would be an example of analog transmission. Analog signals, amplifying where necessary. What about digital transmission? As you would guess, digital transmission, if we transmit digital signals, we consider that digital transmission, but also analog signals. So let's go through an example with analog signals. We have some source connected to B, to C, and to D, the destination. We're going to transmit analog signals across each link, not digital but analog. But let's assume that we start with some bits. A sequence of 8 bits. I've just randomly chosen 8 bits. A has this digital data. To transmit it, if it's going to send analog signals, it needs to convert into some analog signal. We transmit some analog signal. Gets weaker across distance. When B receives this analog signal, it converts it back to the binary value, the digital value. Converts it back. Hopefully, if there are no problems, it will get the same values. And then B takes this digital data and creates a new analog signal and transmits an analog signal representing the digital data. C receives an analog signal, converts it back to binary, and transmits an analog signal to D. And D converts back to binary, whatever the values were. Compare our two examples. In both cases, analog signals are sent all the way. Okay, both use analog signals. The difference is what happens at these intermediate devices. In our analog transmission, we amplify the analog signal to get it across a larger distance. In digital transmission, we convert the analog signal to digital and then transmit a new analog signal. So there's a subtle difference there. That is, we're converting to digital and then generating a new analog signal, that is converting the digital back to analog and transmitting it again. Whereas in analog transmission, there's no conversion, there's no digital processing going here. It's just take the input analog signal, amplify, and you get an output analog signal. Analog transmission, digital transmission. The conversion into binary makes many things easier for our system. It generally makes it easier to fix and detect errors. Sometimes we may get the wrong bit here. Well, we've got ways to detect that they're errors and fix those errors. So it makes errors, can give more accurate data transmission, less errors. It can give things like encryption, although we're not going to talk about it in this course. Sometimes we want to make our data secure. We encrypt it. It's easy to encrypt bits as opposed to encrypting analog data. So converting into binary is good for security in some cases. It's generally digital transmission, whether you're sending analog signals or digital signals, converting everything to digital is generally preferred today. The equipment can be built cheaper and it can operate faster, it can provide security, we can avoid errors, avoid more errors. So generally digital transmission is the preferred approach when it's available today. It's easy to process the bits as opposed to processing the analog signals. I won't go through an example, but we could also do this example with, instead of analog signals, digital signals. But again, the difference between digital transmission and analog transmission is how we process that data at the intermediate points. Digital, always treat it as bits and repeat. Analog, always treat it as analog and amplify. So we get amplifiers in analog transmission and what's called repeaters in digital transmission. That summarises the three cases. Analog transmission always with analog signals, not digital signals. Digital transmission with either analog signals or digital signals. We want to finish this topic today, transmission impairments. So we're going through reasonably quickly. When I'm lecturing, someone at the back, what makes it hard for them to hear? If I turned off the microphone, distance. That is, when I talk, when I don't have the microphone, my voice is at some signal strength, some magnitude. Over distance, it gets weaker. Okay? So the further away the person is, the weaker the signal will be received. And your ears can only make sense of signals at some strength. If it's too weak, your ears will not be able to understand what's being said. That's why someone out in the other building cannot hear what I'm talking about. What else makes it hard for them to receive? Distance, because the signal gets weaker. What else? The medium impacts upon the distance. What else makes it hard for the person at the back to... frequency and medium impact upon the distance. Amplify, no. Again, that's all about the distance. Oh, someone said something. What did you say? No, before that. Not the medium. That impacts upon the noise. If I'm talking, even with the microphone, and everyone else in here starts talking, the person at the back will not be able to clearly hear what I'm saying. Because from communication from me to that person's perspective, that's the real communications, but everyone else transmitting is transmitting noise. So the larger the distance, the weaker the signal gets. That's called attenuation. It's a transmission impairment. It impairs our transmission. And noise is the other major transmission impairment. Other sources generating signals make it harder for the receiver to understand what's being conveyed. The signal that is sent by the transmitter and what is received by the receiver are normally different. And because they're different, it makes it harder for the receiver to understand the correct information. With analog signals, the signal quality is poorer. That is, my voice is weaker with analog signals. With digital signals, we get bit errors. I transmit bits, 0, 1, 1, 0. With transmission impairments, the receiver may receive the wrong bits, and that's bad. So we want to avoid this. What causes these problems? Well, different impairments. Attenuation, we just said, signal gets weaker with distance. That's attenuation. Noise, we just said. Other sources sending signals make it harder for the receiver to understand. And there are a few others which we won't cover so much in this course. Attenuation distortion, which is related to the different frequency components, and similar delay distortion. Although they're mentioned on the slides, we're just going to talk about attenuation and noise. Are the simplest ones and often the most significant ones. Your ears have some capability. They're the receivers. They can only understand some sound above some level. If it's too weak, you imagine that you cannot understand that. Similar, if you receive someone's signal and there's a lot of other noise happening, then again your ears will not be able to understand what's the real signal and what's noise. A received signal should be strong enough such that the receiver electronics can interpret that signal. That's one thing for our receiver. And the received signal should be significantly stronger than the noise received by that device. We have noise, we have some background signal in this audio system, which sometimes is due to this other computer. Two criteria that are important for our receiver. Signal strength must be strong, so it can interpret, and stronger than the noise. In the next topic on transmission media, we'll talk about the relationship between how does the signal strength get weaker against distance and also other factors like frequency, and we talk about how can we amplify, how we can use antennas and so on. But we assume so far whenever we transmit a signal it get weaker across distance. Attenuation. We won't talk about distortion. The other aspect is noise. What causes noise? In this class, what causes noise? Us, other people talking, other transmitters, yes. What else? What else is the noise? If everyone stopped talking, air conditioner. Anything else? Lights make some noise. So all the environment around us, the people moving their feet, the paper moving, electronics, the laptop and so on, is generating noise, or audio noise in this case. Same in our communication system. There are different sources of noise. 4 different cases. Thermal noise, which is due to physics, electrons moving, is present in all systems. We cannot get rid of this. It depends upon the temperature of our environment, the bandwidth, and it can be calculated. It's usually very small. Think of it as some background noise. If we turn off the air conditioner, everyone stop talking, there may be still some small noise, some background noise in the system. So with our electronic systems, there's always thermal noise. We cannot avoid that. Usually relatively small compared to these other components. We often think of it as random. It just randomly varies over time. If we're sending signals which have different frequencies, which we normally do in the same medium, like in this room across the air, then they can interfere with each other and we get what's called intermodulation noise. So the signals can combine with each other such that they interfere with the real received signal and they contribute noise to the receiver. Similar crosstalk is an example. You have 2 cables. Here's one cable and you have it along the floor and a second cable next to it, very close. The signals can interfere with each other and cause what's called crosstalk noise on each other. Sometimes it happens on telephone calls, that you can hear communications or interference from another source when you're talking to someone on the telephone. Interference from other nearby sources. And the 4th cause of noise is some short burst of impulse of noise caused by some electrical disturbance, some lightning, some fault in the communication system. So when we have electronics, if there's some source of electricity that comes from an external location, lightning, some fault in the power supply and so on, that can also create noise on our communication system. It's usually a short duration and usually high magnitude. We talk about an impulse or a peak or a spike of noise. So noise is present in all communication systems and we need to deal with it. We'll give some examples of how noise impacts upon our signals. This first example, assuming we have some bits we want to send. The bits listed at the top. The source computer has these bits to send and they're going to transmit them as a digital signal. So we have a signal which is following some scheme. Let's write it down. A is sending data to B. A has some original digital data, 1010, so on. A is going to create or transmit a digital signal. That's what's transmitted by A across our transmission medium to B. How is the signal created? Using a simple scheme. If we want to transmit digital data 0, we transmit a high level in our signal. Let's say a positive voltage. If we want to transmit digital 1, transmit a low level, say a negative voltage. Just an example scheme to convert digital data into a digital signal. Obvious. When we transmit our system, there's potentially impulses of noise, crosstalk noise, intermodulation noise, and there's always thermal noise. And we can say there's a total amount of noise in our communication system. B receives the transmitted signal. It is attenuated. It gets weaker across distance. And we think of the noise as additive. That is, what B receives is the received signal. Oh, what B receives is the transmitted signal, but it attenuated, plus the noise. And that's shown in this diagram, where this is an example of noise. You see it's randomly varying over time. It's going up and down. There are several impulses or increases in the magnitude. A small one here, a large one here, and a large one here. Maybe due to some electrical fault or some other transmitter in the system. We don't know. Just here, just an example of the measured noise in the system. What is received by the receiver B is the signal plus the noise. And if you add them together, you get this. We see it follows the shape of the signal, the transmitted signal. It's low, then it's high, although it varies due to the noise. And then it's low except for this part, then it's high most of the time, and then low. So you think of the add together and you get the received signal. What the receiver needs to do is get the bits back. We're sending bits from A to B. The bits are at the top. The receiver receives a signal, the signal plus noise here. They need to convert that back to binary. And one approach to convert it is to measure the received signal every time period. If it's low, if it's negative, doesn't matter if it's -1, -1.1 or -0.9, but if it's below 0, assume bit 1. So at this point, this sample point, measure the value. The dashed line is 0. It's negative. Therefore, anything that is negative corresponds to bit 1. So we get bit 1 received. The next sample point, they record the value. It's positive. Maybe 0.8. Doesn't matter the value. It's above 0. And therefore, it's closest to bit 0. It must be a bit 0 received. If anything's positive, it's bit 0, negative, bit 1. Positive, negative, positive, positive, negative, bit 1. Here we record the value, it's positive, therefore bit 0. Here we get a bit error because what's received is different from what was transmitted. That's called a bit error. What was transmitted at this point in time was a bit 1. That is a low value. Sorry, it's this one. Bit 1, a low signal, a negative signal was transmitted, but there's a large spike of noise here. And we see if we add this negative value to this large positive noise here, add them together, and the result is some positive value here. So when the receiver samples this measures this value at the sample point, they get a positive value, and according to our scheme, anything that is positive corresponds to bit 0 here. The receiver doesn't know this. It thinks bit 0 was received. We know it because we know bit 1 was transmitted. That's a bit in error. And similar, it goes okay until the last or the second to last bit, again because this large negative spike of noise here changes our bit 0 into a bit 1. Yeah. The larger the noise, the more chance of errors in our received signal. That's what we see. We see these large random impulses of noise caused errors. Of course, it depends upon the amount of noise, it depends upon the transmitted signal. But in general, the more noise, the more chance of errors. Last 10 minutes, let's give another example. You don't have this one, just follow along. I've generated a signal. In this case, the transmitted signal is a simple sine wave, the simplest signal we can have. 1000 hertz. This is the transmitted signal. I've generated also some noise here. The noise is random, quite small, random, except for this half a millisecond of noise, which goes up much higher than the other part of noise. Let's say if this is an audio signal, this is some student who starts talking in the middle of my lecture. Okay? They create noise on the system. So we have transmitted signal, noise. The received signal in this case is the addition of the two, except I've introduced attenuation. That is, the received signal is no longer plus or minus 1. We transmit it plus or minus 1. It gets weaker over distance, so the received signal is about between 0.5 and minus 0.5. But you still see the shape, except it varies due to the noise. Focus on the grey highlighted point here. Do you think there's an error? Is there an error? The grey highlighted part. Why do you think there's an error? All right. It has a lot of noise. Think this is transmitted. If we focus just on this part, it's the low signal being transmitted. There's a large amount of positive noise. We add them together. The result is shown here. Sometimes it's positive, sometimes it's negative. Depends how we treat it. Let's say if we look at the average value here, I think you'll find the average value is positive. If we took the average value here, then we determine, okay, over this period of time, the average value is positive. The average value transmitted was negative. Something's gone wrong. This noise has changed the level of our signal. So another example of noise. Let's record some values. We don't, let's say we still have bits, so we use the same scheme. If I have a bit 0 to send, I send positive, bit 1 negative. That's similar to our sine wave. If I want to send a bit 0, I have a sine wave which is positive most of the one. It goes up to the peak of +1, or -1 for bit 1. Therefore, what the receiver does to determine what was received is measures the value, whether it's a sample or the average value. If it is positive, assumes bit 0. If it's negative, assumes bit 1. And that's why we'd get a bit error in this case. We transmit negative, we receive positive. We can think of levels. We've changed levels in this case. How many sine components in this transmitted signal? How many sine components in this signal? If I had to write, you have to write an equation for this signal. how many sine functions would you have in it? If you have to write an equation for the top signal, how many sine functions will you have in it? The top signal. Does it look like a sine wave? Yes, it's a simple sine wave. I don't know their signal. That's it. That's the top signal. One component. Okay. Remember yesterday, we removed it. Last week we had signals with 2 components and 3 components. What about this top signal? How many components? The square wave. Go back to your lecture notes. You remember if we keep adding components, and 1 plus 1/3 plus 1/5, 1 plus 1/7, and so on. If we add an infinite number of components, we get a square wave. So the first one in theory had 1, and the current one has an infinite number of components. At the start of the lecture we said the more components, the more accurate our signal is. We had an example over here. We had signals A and B had 2 components. Signal C had 3 components. The advantage of signal C was it was more accurate. It's the same here. Why? See what happens. Signal which is a square wave, an infinite number of components, and in fact an infinite bandwidth. Same noise. If we see and look closely here, we see on average the signal is low, negative, which matches what was transmitted. With our sine wave, our simple sine wave with 1 component, the signal here on average is high. The same amount of noise, 2 different signals, in this case we'll get an error. In the second signal, no error. So this is where we talk about the accuracy of the signal. That is, the same amount of noise impacts on the signals differently, gives a different amount of errors. Let's not go through this one. So, more generally, why would we get an error in the signal? Is it possible to have an error? Yes. Let's say I have this noise, but this spike, or this impulse here, increased. It was very high. What causes an error in this case? An error is caused when a transmitted signal is at one level, let's say -1, but the receiver receives at the other level, or closest to the other level, +1. If the noise was very big here, then it wouldn't be here, it would be somewhere up here, and that would be an error. So the chance of an error depends upon the magnitude of the noise and the signal being transmitted. Let's try and show that in the last 2 minutes. Again, we transmit. I'm just copying over there. Bit 0 was at +1. Bit 1 at -1. Therefore, the receiver has a scheme. Anything that is received and it's between 0 and +1, it assumes bit 0. Any signal received between -1 and 0, it assumes bit 1. That is, anything that is below 0 is one level, anything that is above 0 is another level. So we're saying here. Even with noise, we'd expect that what's received is not exactly +1, it may be vary. So what the receiver says, anything that is close, or the closest to +1 is considered bit 0. The closest to -1 is considered bit 1. In other words, anything that is negative between -1 and 0, bit 1, positive, bit 0. That's the scheme that the receiver uses. Yep.
Why does this should be 0? It doesn't match
Going
the previous scenario.
here, we're saying bit 1 negative value or a low value, bit 0 high value. You could do the opposite. Doesn't matter, as long as it's defined. Okay, it must be defined, this mapping of, I've defined it here. Bit 0, +1. Bit 1, -1. Defined by me. Therefore, the receiver, anything that is received between 0 and +1, assume it's a bit 0. Between -1 and 0, assume it's a bit 1. The final question here. How much noise do we need to get an error? Given this information, how much noise do we need to get an error? What's the magnitude of the noise needed? The transmitter, ignoring attenuation at least, the transmitter sends a signal. Let's say we want to send bit 0. It transmits a signal at +1. If what's received is +1, then we'd see, okay, +1 received, bit 0 is received. That's okay. What if +1 was transmitted, but a signal with magnitude of +0.7 was received? What would the receiver do? Look closer at our scheme here. Transmit +1 volt, receive at +7 volts. The receiver assumes, okay, it's still close to +1. It's within this range. Therefore, it's still a bit 0. Okay, that's correct. Bit 0 transmitted, bit 0 received. +0.1 received. Which one is it closest to? +1 or -1? +1. It's still within this range. Still greater than 0. So therefore the receiver assumes 0, bit 0. That's correct. -0.1 received. -0.1 is closer to -1 than +1. That is, it's within this range, between -1 and 0. It's negative. Therefore the receiver assumes, okay, it must have been a bit 1 transmitted. There's our bit error. Similar if it was -0.7 or even -1. That is, if there's noise which has a magnitude of 1 or more, in this example, we'll get a bit error. That is, it takes our +1 to negative, a magnitude of 1. Similar the other direction, if we transmit -1 and it goes positive, that'll be an error. So the magnitude of the noise the magnitude of the noise impacts upon the chance of an error. What we'll show tomorrow is that the signal also impacts upon the error. Tomorrow we'll look at another signal and see how noise impacts on this signal. Let's continue that then.